Hi guys, I'm Jayashri and today we'll be looking into NAND2TETRIS Project 1 and 2. So in Project 1, we have elementary gates, 16-bit variants, multi-way variants, and all that stuff. So we'll look into them one by one. So before going to that, we have to download the hardware simulator, which is I pasted the link of the website here. So otherwise, you can just type NAND2TETRIS. And you can go to this page, which is the software. And right here, you can download this software suite, NAND2TETRIS software suite. And also remember that you have to have any Java runtime environment, JRE, to use this. So you can download in this link also if you don't have that one. So going into the downloads, you will be having and a zip file, and you have to extract it. And once you extract it, you can go to Tools and Hardware Simulator, and there you go, the Hardware Simulator. So we're going to perform all the simulation in here. So in NAND2TETRIS, of course, we're going to build everything from the NAND gate. So we have the NAND gate and the truth table right here. So let's build the elementary gates using NAND gates. So NOT gate. So how do you build a NOT gate using a NAND gate is given here. So it's that simple. So let's see the code. This is called HDL file. We'll be writing the code. There are basically three types of files, namely HDL. And we have CMP file, also TXT file, TST file, which is text file. So in HDL file, we'll be writing the code. So it's simple. NAND A in and out is equal A in, and B also you'll have the same in. So if we can compare this with this, we'll understand it more easily. So there's that. So when you simulate it, choose the right project and NOT gate, and for the script, again choose NOT gate script. You can run it. Output, you get the output. So if you want to compare it, there is a file which has the correct truth table for all these elementary gates and stuff, and all these projects. You can just compare it there. So there's no change in the output in the comparison. So the next gate is AND gate. So for the AND gate, the truth table and the circuit diagram is given here. So in terms of NAND and NOT gate, now that we have NOT gate, we can use NOT gate rather than using NAND gate and making it redundant. So AND gate. So if you look at the code, you can understand the code. So we have a NAND gate where the input is sent and the NOT gate and the output sent. So this circuit helps us to understand it better. So again, we can choose AND gate, the script. But we get the AND gate's logic or truth table. We compare it and it's one and the same. Next we have OR gate. Again, OR gate is just the circuit. So let me show you HDL code for that. So HDL code, again, it's not and NAND. Comparing it with it, you can see that it is really easy. So right here, NAND gate is replaced by NOT gate, of course. It's simple rather than being redundant again. So executing OR gate. The truth table is correct, and when we compare it again, it compares well. Next is the XOR gate, and I've given the truth table in the diagram right here. So this is how I'm going to make it rather than using NAND gate. I'm going to use NOT and an OR gate and make it simple. So So if you take a look at this, we've got the XOR gate, not, and or, just follow through with the inputs and name it with different names and give it. So when we simulate it, here we get the output, and when we compare it, that's right. So next is a multiplexer. Also, in simple words, multiplexer is many inputs and single output. So it's a selection operator. So we have the select and the inputs. We're not going to confuse with the enable right here now. So for the multiplexer, we have got the circuit using a NOT gate, AND gate, and two AND gates and an OR gate. So so we've got not and or. So looking at the circuit and the code right here, we can understand what is happening there. And then you execute it. The output and the compare is yet again the same. So next is demultiplexer. It's actually single input and many outputs. It's the opposite of the complement, let's say, of multiplexer. Not exactly the complement, but the opposite. So this is the circuit diagram for the demultiplexer. So if we take a look at this, we can understand with how we are using the select and A and B with not and getting the answer. So let's simulate and check if compare it if it's right. The output, then we compare it and again it's right. So next we go to 16-bit variants. It's actually quite simple. So we're going to see four, not 16 and 16 or 16 and MUX 16, that is multiplexer 16. So bitwise operation is being done right here. So it's simple. We use a array-like structure called bus in HDL. Let me take not 16. So this is not 16. So in not 16, we've got, so here is the bus. This is called as a bus. So we use an array-like structure, and we are going to do bitwise NOT operation for each of these 16 bits from 0 to 15. Let's simulate and see if it's right. So the output, the compare, and it's one and the same. So for AND, we've got the same bit by bit operation with AND. So if we take a look, just add. And here, so we have got the same bus, and we are taking the output by, we have two inputs here, of course, because it's and we are bit by bit, we are performing the AND operation, and we are getting the output. So AND 16, but 16-bit variant. So the output and the compare, both are one and the same. So next we have OR 16. So our 16 similar. So let's have our 16. Again, the output and the compare is same. So at the last, we have MUX 16, so 16-bit multiplexer. So again, it's performing multiplexing bit by bit. So let's run it. This is the output, and the compare is again one and the same. So here it ends. Next, we go to multi-way variants. So it's actually different from the 16-bit variant. So in this multi-way variant, we're going to have like, it's not bitwise. It's an 8-way OR. I guess with the code we can understand it better. So it's like, so if we have a 0 to 7 bits, which is 8-bit, so we have we'll perform OR operation for 0, 1, and then 1, 2, 2, 3 consecutively. So and the resultant would be the answer. So the code for this is also quite simple. So this is it. So we are performing OR operation for the first input and the second first bit from the left, and this, I mean from the right. Okay, we are performing OR operation for the first bit from the right and the first bit from the second bit from the right. So it's 0 and 1, and we're getting the output. And this we are using, and we are comparing it with the second bit in the second position, then the third position, fourth position, and we're repeating this, and until we get we compare all the digits, we perform our operation to all the digits and the corresponding outputs. So let's just check. This is the output. Just compare again, both are one and the same. So next we have multiplexer 4-way 16. So we can use the already constructed 2x1 multiplexers. But here, what is the difference is that we are going to use 16-bit variant. So we'll have to use our MUX 16 to do this. So 4-way. So if we take a look at this, we can understand that this MUX 16 is actually 2x1 multiplexer, which we did earlier, and then we are following the circuit diagram and we're getting an answer. So yes, so the output and the compare are one and the same. Next, we have 8-way multiplexer, again 16-bit variant. So 8-way multiplexer, if we look at this, we've got this 4x1 multiplexer 16-bit variant previously, just now, and we are using that and the 2x1 multiplexer, and we're getting the answer. So we here, this is called sub buses. We use it to take like subsets out of these buses. So when we execute it, this is the output and the compare file. There's no change, it's one and the same. Next is demultiplexer 4-way. So this is not a 16-bit variant. So we're just going to follow this circuit diagram. So we are using the already done 1x2 demultiplexer, and we are giving or getting the answer for the 1x4 multiplexer. So when you simulate it, the output and the compare is one and the same, so the code is right. Next is the demultiplexer 8-way. So again, we can relate it with the previous question of the multiplexer 8-way 16 variant. So using this circuit diagram, we use 1x2 demultiplexer and 1x4 two 1x4 demultiplexers, and we're getting the answer. Again, here, if we are using sub buses, this is the output, this is the compare, and it's again one and the same. So with this, our project 1 for NAND2TETRIS is over. So let's move on to project 2 of NAND2TETRIS. So here we're going to see half adder, full adder, add 16, increment 16, and ANU, which is the arithmetic logic unit, of course. So half adder, this is the truth table. We have the sum and the carry here, 2 inputs. We'll be adding this. And so we're going to use an XOR gate and an AND gate, and we're going to get the answer. We're going to, so in this whole project unit, we'll be using the gates, the chips we have built in project 1. So when comparing here, we can understand that we're using the XOR gate to get the sum and the AND gate to get the carry. So when you simulate it, going to project 2 for the simulation. Half adder. This is the output, and this is the compare. Both are one and the same, and we can move on to the next part. So this is the full adder. So for full adder, rather than using the normal gates, we can use the half adder. Again, to avoid redundancy. So we've got the 2 half adders and 1 OR gate to get the carry. So in this code, we can understand that we are using half adders and an OR gate. So let's check if ours is right. So the full adder code is executed, output of the full adder, and when we compare it with the inbuilt output, we get the same. So full adder is right. So next is add 16. So it's quite simple. We are trying to add 16 bits. So just like how we did with OR16 and AND16, we're going to use the full adder, but the first one you can use the half adder. That's not really an issue. Anyways, full adder or half adder, for the first bit, you're going to get the same because the carry is not there. So this is the code. So when you simulate it, This is the output. When you compare it again, you're getting the same answer. Next is increment 16. So whatever number you've given, 16-bit number, you're going to increment it by 16. It's also quite simple, and the code is very, very simple. So if we take a look at this, what we're going to do is we are using add 16 that we just saw now, and we are going to have bus of B of 16 bits, and the first or the rightmost bit would be true, as in 1. The other bits would be 0. So we are adding ones in the 1 in the 0th bit of A, and the output would be the incremented value. So let's take a look at it. Running it. This is the output. When we compare it, we are getting one and the same. So next, we are going into arithmetic logic unit of ALU. Actually, it has a pretty sophisticated and a very cool algorithm which makes it a function. So this is the table. So to perform all these functions, actually these are few selected functions. So to perform all these functions, the ALU supposedly follows these rules, and we can get it. So if you can try it out, it's actually pretty cool to find that you get the answer. So to perform the ALU, this is the logic gate I've used. So in here, I also needed or 16 way to perform it. So I have created a 16 way. So using this R16 way chip, I can get the ALU. This is the ALU code. Using MUX 16, not 16, and then add, you have and all this stuff. And using the given circuit diagram, we can very well create the ALU. So let's check if the code we have done is right for this ALU. So the code has run. So this is the output, and this is compare, and we can find that these are one and the same. And with this, project 2 is over. So we've seen NAND2TETRIS Project 1 and Project 2. Thank you so much for staying along.